design, and it'll basically just program your database for you, and it's super easy. Yeah, but I'm getting way off topic, so let's get back on topic. Okay, so here's how we draw a table. What we do is we give it a table name, so we put the table name either right here in a complete column like that, or just right above it. So we'll just put it up above it right now. So this is a user table, and then what we can do within here is we put the columns this way, vertically. We write them horizontally, but we list them this way. We're not putting them across here. Because if we put them across here, we would assume that we're going to have row value, like Caleb, password is awesome, email is legit, or cool, and then like password, I already said password. But we're not doing that, we're just going to put the columns. So the first column we could have is user ID, because we're just going to use a surrogate primary key in this example. So you could have user ID. Now, when you get into it, you can also put other things like data types in here and any other restrictions you have, such as not null if you wanted. But for now, and for most of the design, for design concepts, I'm not going to do that because I'm going to be writing the same thing over and over again. And you kind of only do that when you're finalizing your database. So you can kind of worry about the data types later on, but for now we're just going to get the columns, figure that out. Good. We'll go from there. So user ID, username, the password, and so forth. Hopefully you guys can read that, probably not. And then what we do, if we want to create another table, guess what we do? Oh, we just draw another box, right? And we connect these with lines, and we can, there's certain ways to draw lines that represent different relationships. Like that's one way to do it. Or we could have like, yeah, you get the point. Oh, I found a nice big piece of chalk. Cool. Alright, so that's how you do that. Now, that's pretty much all the basics of entity relationship diagram drawing. Just remember, we put these in here, the columns, and what we can also do if we wanted, we could put indexes down here. We could put like index types, and then we could also draw our relationship types with different lines, and we can draw our foreign keys by either putting them down here or doing some other kind of thing. Now there's also other conventions you might have heard of or have used, like UML and other design techniques, and I'm not saying those are bad, I'm just saying this one's super easy for beginners and for experts. We actually talked about this a little bit, but we haven't really designed it or anything because now we're talking about actually drawing out databases. Cardinality is basically the relationship type between a row of one table and rows or a row of another table. So I thought of the best example I have for this is a credit card database. So like basically a credit card company has a table for credit cards and then a table for card holders or the people who order the credit cards and use them to buy things, and basically they're the credit card company's customers, I guess. So I will draw those tables out just so you can see this. I'm not going to draw them real big or anything, but just so you see how the connection works. So we have the card holder, and then over here we have the card. And there's some kind of relationship between these two tables. Now, the only two possibilities for cardinality are one or many, obviously for both sides. So you can have one to many, or many to many. Those are the only three possibilities. Now, another thing to think about when it comes to many, you might even consider that as not a possibility because you'd have to have an intermediary table, which we talked about that when we talked about designing many-to-many relationships. When we're talking about many-to-many relationships here, it's logical, which what I mean by that is we're drawing it as just like this, and we would say many to many, and then when we actually implement that in a database, we would have to have a card holder, card holding table, and then the cards table. That would be how to draw a many-to-many relationship. So hopefully that kind of makes sense for that. So in reality, when you're actually drawing out finalized products of databases, the only possibilities are one-to-many or one-to-many. Because even if you have an intermediary table, this is going to be a one-to-many relationship and then a one-to-many relationship. And there's a certain way to draw those out. That's what I'm going to be drawing right now. So a one-to-many, it's pretty simple. The one side, all you have is a straight up and down line like this. The many side, you have this. This thing that we're doing right now is known as crow's foot notation because it looks like crow's foot. I think that's why they call it that. I don't really know. But this is a one, this is a many. So when we're drawing it, one, many. We could also have one to one, of course. So that's another possibility I forgot to mention. One to one. Now before we start drawing it on both sides, I think it's easy just to think about one side. Like think of a card holder relationship to a card. We would have one card holder. Now that we have that side figured out, we just think about the card holder. Then we can add in the card, and we have many cards. So one card holder can have many cards. And that's how you would design the line between the tables. Like that. Now there's another thing we need to talk about known as modality, which we'll talk about in the next video, but for this we're just going to keep it simple. Just drawing these things here. But you might see also like circles. You might see a circle here, for example. We'll talk about that in the next video. So now you know how to draw a one-to-many relationship. So what does this exactly mean? That means one row can be connected with many rows in this table. It's not necessarily the table, but the rows within the table. So we could think of a specific card holder. We could have a card holder with the name Jack, an ID of 2, and we could have many rows over here, cards. We could have a card with the ID of ID 6, ID 8, ID 12, and you can see this guy has a lot of credit cards. So all of these rows can be connected to an individual row within the card holder table. Now let's look at it the other way. We could have a many-to-one relationship, or basically a one-to-many going the other direction. So we could have this. So now one card can be connected to multiple people, but multiple people can't be connected to one card. I'm sorry. One card can be connected to multiple people, but one card holder can only be connected to one card. So that means one person cannot own more than one card. So now we think of it the other way around. We have a card with the ID 3. We have a card with the ID 4. The ID of 6. It doesn't really matter what the numbers are. And then we have a card holder. We just got a guy named Jack, which ID of 3. And then we got Bill, ID of 2. Well, we can have one card attached to many people. So this card could be attached to many people, which means these people co-own a card. They're both the owner of one card. But now you have to realize an individual card holder can't be connected to multiple cards. So Jack cannot own another card. That's not going to work out. If you wanted that to work out, then you'd have to have the intermediary table, which we talked about in designing many-to-many relationships. And this video is less to be a review of relationships, but more of how to draw them. So you have to realize the difference between all of these possibilities. One-to-one, one-to-many, or one-to-many. It just depends on the actual application. Modality, it's basically whether or not the child is a required child, if the relationship is required. We talked about that when we talked about the column characteristic not null. So, think of it like this. We have a credit card company. We have a table for the card holder. And then we have a table for the card. Obviously, the card holder, the ID for the card holder, the person who owns the card or buys the card from the credit card company, they're going to have an ID, and that's going to be a not null column, meaning it has to have a value. That is obvious because it's going to be the primary key, surrogate primary key, and it has to have a value. So we have like this guy, and he has an ID of 7. We have another guy with the ID of 12, and then 368, and so forth. Those are IDs, you see? Card, that is going to have a column, which is a foreign key, referencing the card holder, because the card is the child in this relationship. So the card holder has the primary key. Can you see that down there? Yes, you can. Card is going to have a foreign key, which connects to these. So this is going to be a foreign key, meaning these are the people that own certain cards. So we have a card with the ID of 12, we have a card with the ID of 48, I'm just making up numbers right here. We have a card with the ID of 98, we have a card with the ID of 112. Well, they each have an owner. You see, this is the owner. And this is a foreign key which references the primary key. So 7, this card's going to be owned by that person. 7, this card's going to be owned by that person. 7, this card's going to be owned by that person. So all of these 3 cards are owned by that person. 368, that's going to be owned by somebody else. Now, if we gave this column right here, the foreign key, basically the card holder column, because it's a child, if we gave it the column characteristic not null, it would be required that every single row has an owner. That means we can't have a card in here that is either not activated and doesn't have an owner, or we can't have a card in there that is not being currently possessed by a card holder. Because you think if you have a credit card, somebody owns that credit card. But when you first make a credit card or something, or if you if you get rid of the credit card or something, it might be a credit card that currently does not have an owner. Does that make sense? So basically just a credit card that's not being actively used or is disabled or something like that and does not have a card holder. Well, if we wanted this database to be able to store cards that don't have owners, we would not want the not null characteristic because that's going to prevent it. So that's kind of how that works. So if we take that off, then we could have a card down here with the ID of 101 that doesn't have a card owner. Well, I know we've already explained this all, but now let's talk about designing. So let's just make this simple. We'll pay attention to the, we'll say one card. Well, this obviously is we're going to talk about a one-to-many relationship, meaning one card holder owns many cards, and we're also going to be talking about a one-to-one relationship, meaning one card owner owns one card. If we want to do a many-to-many, we just need an intermediary table. The same concept kind of applies, but we don't necessarily have to go through that. Just break it into a one-to-many, two one-to-many relationships. Alright, so let's try this. So we have, over here we have the table. That's going to be the card owner. Over here we have the table for the cards. And there's a relationship between these two. That's a really big gap, but whatever. So let's start over here. We can say one card holder, because that's what we're just going to say, one card holder for each time. Let me bring this in some so you can actually see. One card holder can have one card. So what we just did is cardinality. We talked about this in the last video. Now let's do another example. We'll just do the same thing, and you'll see why in a second. Let's do another example. And then finally, one more example. Running out of room here. So we have the basic relationships. Now we can add one more thing to say if it's nullable or not nullable. Basically, does the child, this is the child, which is the card, we're asking, does the foreign key column have the not null characteristic? So we have the possible relationships, one to one, one to many. Now, what we're going to do is we're able to add the modality in. And the way we do that is we add either a little circle or a little dash. Or you can think of it as a 0 or a 1, which actually will make sense, and you'll see why in a second. 0 or a 1. So, over here we have the card holder, one card holder for all of these examples, and then over here we have the card. A 0 means the column does not have the not null characteristic, meaning it accepts no value. So, this is saying it can accept no value. So, we have a 1-to-1 relationship, that's the maximum. The card holder can have up to one card, but it's not required. So, 0 or 1 cards. 1 or 1 cards. 0, at least 0 cards, because you can have up to many, or at least 1 card. So, this means not null, not null. Now when we design this, we're talking generally from table to table. So we would have card holder, and then card. And why do I have to say that? Basically because if we have a 0 here, that means there's not necessarily going to be a relationship between a certain row. So when we're talking about rows, we might not actually draw a relationship between certain rows. When we draw relationships, we talk from table to table. And those relationships explain what rows can have relationships with different rows. So in this example, let's just focus on the top one just to make it easier. We would draw this within our database application. We would say we have the table, card holder, and then that has some kind of relationship with the table card. Now we could say one card holder can have 0 up to 1 relationships with one individual card. So we have a card holder with the ID of 7, and then we have a card with the ID of 68, owned by the card holder 7. So that points back, and that's acceptable. We could also have a card, 69, and we could have a person 8, and we could say, oh, it doesn't have an owner. That's fine. We could have another card 70, and it can have the owner 8, which points back to 8. And then we could have another person, which could be 87, and we could have a card 63, which has the owner 87, and that points back to the owner 87. So that's how those relationships work. Now, at first these can be kind of confusing, so just practice. Make sure you fully understand how each one works. Just review. We could have, here's 4 possibilities we could have. Let me put that one up there, it makes more sense. One card holder can have 0 or 1 card. One card holder can have only one card, because you can have one the least, and then up to one, and then you have one card holder 0 or more, and then one card holder 1 or more. These two are required, meaning every single child has to have an owner. Or every single card has to have an owner. Every single child has to have a parent. So hopefully that all makes good sense. I just want to introduce a topic, so in the next 3 or so videos, when we go over it, it's going to be like kind of not all new to you. You'll kind of have an idea of what's going on. So we're going over what's known as normalization. So normalization is a process where we go through our database plan that we have, and we start correcting things that may cause data integrity problems, or just repeating data, etc., etc., whatever you want to say. The normal forms are basically like a checklist that you're going to follow, and when you get to the end, you'll have a pretty good designed database. So yeah, there's 3 main forms, and these are named very conveniently, I have to admit. First, normal form. Second, normal form. And guess what the third one is? Yeah, you guessed it. Third, normal frame. I'm kidding, it's form. That'd be weird though. Alright, so we got first normal form, second normal form, and third normal form. These are the 3 steps of normalization for databases. Now, if you really want to get into database design, and you're just like, man, I love this stuff, I gotta get more. Well, there's tons of more steps you can add and make things all complicated if you really want. But for our practical purposes, these are the only 3 that you're going to really need. And I know there's like a glare right here because of these lights. And I know I'm just working on it. So give me a couple videos and I'll try to work on my lighting a bit. But for now, first normal form, second normal form, third normal form. Why do we have these? Well, it's because we want a systematic way to follow to produce a normalized or a good structured database. Alright, there's a couple things you should know when it comes to normalization. We still have to talk about the idea of things being atomic. We want everything to be atomic. You also have to kind of think about data depending on other data. So if you think of like, let's say a primary key, you got 608, just a number, that could refer to anything. That could be a person, an order, an event, whatever it is. It's just a primary key. And that also is going to have different columns in the table, which have different attributes about whatever this thing is. So let's say it's a person, and we have a column for the name. And let's say this dude's name is Caleb. What a dumb name, right? This depends upon the primary key. So what I mean by that is if we change the primary key, we're going to also change the person, right? So let's say we have 609. Well, this is going to be a completely different person, right? Because they're 2 separate entities. This one's referring to some guy over here, and this one is referring to some guy over here. 2 separate entities. You can also think, oh, by the way, that process or that thing, this is called dependency. So the next 3 videos we'll be going over the first normal form, second normal form, and the third normal form. The other main thing is that these are kind of comprehensive, I guess you could say. So what that means is, once you have a first normal form, now you can go on to the second normal form. But you can't go jump in right here. You have to have it in first normal form before you can get into second normal form. Same thing for second normal form into the third normal form. So that means if you have a database that is in third normal form, it is also in second normal form and in first normal form. So I know I'm just like getting all this technical on terms and junk. So if it's freaking you out, don't worry. It's really simple. Gotta get my hair out of my face. Alright. But basically, it's a list of steps, a list of things to do, and basically you can't do this step 2 until you do step 1. So this here, second normal form, that's step 2, Can't do this until you do that. So you gotta go through the process. And then once you're at third normal form, things are good to go. This video will be over the first normal form, which is the first step in database normalization. This normal form deals with data being atomic, or atomicity. Alright, so let's begin. Let's first look at 3 examples where there are problems, and then I'm going to explain a solution. If we take a look at this first example, we have a user ID, first name, last name, email, and address. I have some values in here, but those aren't really important in this example. The main thing you need to pay attention to is the address. Because an address, if you think about it, actually consists of a street address, a state, country, and so forth. So this column is not atomic. We're asking for multiple things within one column. So that is the problem in this example. The solution for this one would be to break it up into multiple columns, a state, and so forth. That way we don't have a bunch of things within one column as an individual value. This example, you can see we have one row with a user ID, first name, last name, and email. But if you look closely, we have 2 emails. These emails were entered together as one individual value. So you can think of maybe on a website it'll ask you for your email. Imagine putting one email in and then putting your second email in the same box and clicking submit. Well, it's entered into the database as a single value, maybe with the comma or something, but it's still entered in as the email for this user. So 2 values within one, which is not atomic. In this example, the actual values given for the email are atomic because they're only one email, but we put 2 entries within our database. So now we have this in here twice, this in here twice, and this in here twice. And the primary key should never be in there twice. The only time you can see the primary key in there twice is if it's a reference as a foreign key, because a foreign key can be put in there multiple times. But the primary key of 5 should only be in there one time. So we have all that duplicate data. Now what if this Caleb Curry goes and gets a name change? Because that's such a dumb name, right? No, I'm just kidding, because that's my name. And I actually like that name. But anyways, if he gets a name change and he updates his information, what if only this one's updated? So now we have conflicting data. And see, that's the problem with data integrity. We need to make sure that doesn't happen. So in this example, the column is the problem. In this example, the values for the row is the problem. And in this example, the values for the row is the problem. So these basically have the same problem. How do we figure out the solution? Well, let's take a look over here, and as you can see, there is no solution. So yeah, guys, thanks for watching. I'm just kidding. Let's do this. The best solution for this problem is to have a user table, and I'm going to write the columns that are within this user table. So we would have a user ID. Then we are going to have a first name, and we're going to have a last name. If you wanted the address in there, you could have street address, state, country, all that other good stuff. Then we're also going to have an email table. So the solution is to break off the problem column. You can see in this example, the email is the thing causing the problem. The address that we had earlier, that's fixable. If it's a problem in the column, we could just break that up into multiple columns. So we wouldn't have to make a new table for that. But since this one, even though the column's correct, it's the values within it that's causing the problem, we would need to create a new table for that. So that's why we have this email table. And now within here, we're going to have an email ID. And then we're going to have a email, which is going to be the actual email address, which in this case would be these. And then we're going to have a user ID. Now this is going to be a foreign key that references this user ID, the primary key of the user table. Now, if we wanted to put 2 individual emails, we could have rows within this email table. Let's spread out the email table and see what it might look like. Here's what the email table might look like. We would have an email ID, which is just a randomly generated number for each email. 608's fine. And then the email, that's going to be the actual address of the email. So we could have this. I'll try to make it just as bad as handwriting. Perfect. Then the user ID of who owns that, which in this case would have been 5, because 5 was the ID that was used for this user. This will be our first row. Then we could have another row, and it'd be a new email, so we'd have a new email ID. It'd be a different email. We would use this one this time. And I'm going to make that beautiful handwriting that you guys love. There we go. And then the user ID for that would also be 5. Now, this repeating value is okay. This repeat right here, this is okay because this is a foreign key. And multiple emails are allowed in this situation. This email ID, this is not okay to repeat because each individual number should be a separate email because this is the primary key of the email table. Now when we look back at the user table, we don't have any repeating data because we're only going to have a user ID such as 5, first name, Caleb, and a last name, Curry. And there's no need to make a repeating row because we have all the information we need without having any problems. If we change the name, we would just update this, keep the same ID, change this to whatever we name ourselves or whatever the person names themselves. So there you go, everybody. That's first normal form. Now, second normal form deals with what's known as a partial dependency. That's when a column only depends on part of the primary key. So in order for it to depend on only part of it, you have to have a compound or composite key. So basically the primary key has to be multiple columns. Because think, if you just have one column as the primary key, a column can't partially depend on half of it. Does that kind of make sense? I don't know, maybe not. Let's say we just have a random table for people. So we have, the persons, let's just use a person ID. And we have some attributes about this person. We have their name, maybe their phone, or their pH level. And maybe their email. Let's first talk about what a dependency is before we go in and talk about partial dependencies. These columns depend upon the primary key. So in this case, this is the primary key. And there's a dependency here. Another way you can think about it is if we have another table about cars, we could have a car ID, which is also a surrogate key. Now this person's name, it does not have a dependency here. You can see this name is only dependent on the person ID, not upon the car. So this doesn't make any sense here. Another thing is that the person ID doesn't have an unrelated entity or an unrelated attribute about the car ID, so such as the car color. The car color has a dependency on the car, not the person. This isn't going to make any sense. That's what a dependency is. Now, what is a partial dependency? So let's see what a partial dependency looks like using surrogate keys. You'll see this when you have a many-to-many relationship broken up with an intermediary table, which is the correct way to design a many-to-many relationship. So let's think of the example of books and authors. Because if you think about it, one author can write many books, and one book can be written by many authors. So conceptually, it's a many-to-many relationship. But we're going to store that in the database as one-to-many relationship on one side, and then one-to-many relationship on the other side. So we get this look at the table, intermediary table, and then a table. So over here, let's put the authors. So this is the author table. Then over here we have the book So this is the book table. And then in between, we have the intermediary table of book authors, or book author. So this is the correct way to design it. Now when it comes to attributes, all the attributes about the author are going to go over here, all the attributes about the book are going to go over here, and all the attributes that have to do with both the book and the authors connected, those will go in this table. So first let's give them some surrogate keys. We'll give this one an author ID. We'll give this one a book ID. And this one's going to have two foreign keys of the author ID and the book ID. And those foreign keys together will be the key for this table. So that's kind of how you would set this up. Now things about the author go over here. So you know, their first name, maybe their last name, maybe their birth date. Whatever you want to put about the author. The book would have stuff about, you know, the ISBN, which is, the ISBN is the code on the back of a book you can look up. It tries to uniquely define that book, so the exact edition and everything else, so you can just use that to define it. You know, we would maybe have the page numbers or the publisher. The publisher could be a primary key or a foreign key to another publisher table, or you could just have it in that table if that's how it worked, but likely it'd go to another table. But we're getting off topic. Anyways, it would look something like this. So author information goes over here, book information goes over here. This is the correct way to design this table because when it comes to dependency, the first name of the author has only to do with the author and it has to do all about the author. Now let's look at things that have to do with both the book and the author. We could have something such as the author position. Now what that is, when you write books, often there's a person who has like the first author position, which is what the big name is, and then you'll have the second and the third and the fourth. People often compete to try to get first author. This has to do with both the book and the author. Because if you think about it, if we put author position here, that's going to depend on what book we're talking about. We can't just put author position 1 and say he's first on every single book he ever is going to write. That doesn't make sense. We can't just say author position 1 on the book because it doesn't say which author we're talking about. Which author is 1? It doesn't make sense. That's why we have to have it in this table because it has to do with the book and the author. So we could say book ID is 17, author ID is 22, and the author position is 1. So that would say the book with the ID of 17 and the author with the ID of 22 is in the second or the first position on that book. It's a little complicated, but we combine that with joins to make more sense for the actual viewing of the data. But anyways, this relies on the book and the author ID. That's why it's in this table. This is correct. Now an incorrect thing would be something like the ISBN, because the ISBN has to do with the book only. So when you look at this, it relies upon the book ID. It has a dependency on the book ID, but it doesn't have a dependency on the author ID. This is an example of a partial dependency. Now the correct way to fix this, in this case, would just to be to take ISBN and put it in the book table, which we obviously already did, because I put that in there first when we started. But if you didn't have this table and you're working with just say like one table maybe, well then the correct way to do it is to take the book ID, the ISBN, drag them to another table, and then use a foreign key to connect to that table, which we already have it structured correctly because we understood how to design that many-to-many relationship, which is why relationships are useful to understand. But if you don't have it already set up correctly, you'll have to take the partial dependency and move it to another table and reference it with a foreign key. For second normal form, you want to first be in first normal form, and second, remove all partial dependencies by moving the columns as we did here. We took that ISBN, put it in the correct table. Now another thing you can think about is if you have a table where there's a primary key of only one column, you're already in second normal form for that. Like imagine it for this. How can birth date be dependent on only part of the primary key, which is author ID? Because there's only one. You can't depend on only part of an individual column. Third normal form. In order to get there, you have to first do first normal form and second normal form. So it's kind of like a ladder. You can't just start at third normal form. You have to work your way up there. So this one deals with what's known as a transitive dependency, which is when a column depends upon a column which depends upon the primary key. So I know that's kind of like confusing, so let me just kind of draw it out in a table. It'll make a lot more sense. So here we have a review table, as you can see. I'm kidding, you can't see, it's just a square. So we could say review. So like this could be on a website, it could be, you know, like a shopping website where you review a product, or it can be a review on a video or anything really. It could be a review on a book. Most likely it'll be on a shopping website where you buy something, whether it be a book or anything or cars or whatever. It doesn't matter. But in this you would have something like a review ID, obviously, which will be the primary key. You would also likely have what that review is, like in a text form, so like a comment. So you would have the actual review, and then you would have maybe a star rating or multiple star ratings. So you could have a star rating, so maybe 1 through 5, 1 being the worst, 5 being awesome, and then 4 maybe being like really sort of okay, you know? And then we might have something that has a star meaning. So that would be like, sort of okay, right? And finally, we might have something like either a user or the poster. I'll just put the user because likely you will have some kind of user account on this website where you can post comments. So this will likely be a user ID, and it will be a foreign key to a user table. But we're not going to put that in here right now because that's unrelated to the actual point. So foreign key, primary key. Now, let's look at right here. We have an issue. This is what's known as a transitive dependency, because the star meaning depends upon the star. And a way you can kind of try to figure out if it depends on it is, okay, well, if we change the star, is the star meaning going to change? Well, if we take the star and we change it from a 4 to a 3, it might go from really super okay to really average. So the star meaning is going to change. So that's a dependency. But then the star actually depends upon the actual review ID. Because if you change the actual review, the star is able to change. So this is known as a transitive dependency, and it is bad. Now you can also have a multiple transitive dependency, which I don't even know what those are called. But that would be where a column depends upon a column, which depends upon a column, which depends upon a column, which depends upon the actual primary key. And it can go on forever for as long as you want. But you don't want it because it's bad, which is why we're going to remove it. So to remove this, you take the columns that are causing a problem, you move them to a separate table, and then you create a foreign key in replace of them, which references the actual other column. So let's do this. So since these columns right here are the ones causing the main problem, we take them, we put them in their own table. We have a star table. Within the star table, we're going to have a star ID. And then we're going to have the actual star, whether it be 1, 2, 3, 4, or 5, or whatever kind of rating system you're using. And then we're going to have the star meaning. And then over here, we're going to replace these columns. Let me make this a little prettier. And I just made it 5 times worse. But we're going to replace that with a star ID, which is going to reference this table over here. So now we don't have that problem because the only column over here is star ID. We don't have the star meaning, which was the real column that was causing the problem. Now over here, we could have, if we drew out this table, we would have, we could have a star ID of 3, and that star could be a 3-star rating, and it could be, it could mean average. Now, we're likely to only have 5 individual rows in this table, so it's kind of like a reference table. So over here, we could have a star ID of 1, 2, 3, 4, 5, or 0, 1, 2, 3, 4, or 5, 6, 7, 8, 9. It doesn't really matter what the ID is, because the ID is just a number used by the database and has no real world value. So we would have 5 rows in here, and then we would reference them in the reviews table. So we could have, okay, this is too ugly. Let me just explain it. We could have one review with the star rating ID of 5, which could correlate to a certain rating from this ratings table. That's the main idea of the third normal form, is to take those transitive dependencies, move them to a new table, create a foreign key to reference that table. So in review, first normal form is making everything atomic. Second normal form is removing any partial dependencies. And then third normal form is removing any transitive dependencies. This video we will be discussing indexes. The best way to think about it is just to take a book, look in the back. There's often an index here, which basically has a huge list of topics, and it says what page they're on. So you'd be like, oh wow, that looks fun, queries. Go to page 2078. Wow, it's right there. I found that so fast. I didn't have to go search through the entire book to find it. That's an example of an index. It's basically a list of where certain data points are. Another kind of index is, you can think of a phone book. You go to a phone book and you search through the phone book, you find someone's name, we go to grandma, and it'll have their phone number right there. That's another type of index. It's where the data is sorted in a way that you can easily find it and the data is right there, versus an index in the back where it's a list of data pointing to where it's at. The one we first discussed is known as a non-clustered index. What that means is that the data is not actually where the index is. The index is a separate thing, and it basically just sorts the data, and it's basically a point that tells you how to get to the data. So the way it works in a book is you find the topic, and it'll tell you where to go. 365, for example. Go to page 365. That's a non-clustered index. A clustered index is like the phone book, where it actually reorganizes the actual data in a way that's easy to use. Non-clustered points to the data. Clustered organizes the actual data. So we can have multiple non-clustered indexes. That's because a non-clustered index is basically just a list of references that point you to the data, so we could organize it in different ways. But as for the clustered index, we can only have one of those. That's because it actually organizes the data that way. So think of a phone book, it's organized A to Z, or however. You go through there and you find it. That's a clustered index, it organizes the data. Well, what if I wanted to put the data in by the phone number? So the smallest phone number, like 0000001, which would be an awful way to organize a phone book at the beginning, and then 999999999 at the end. That's an awful way to design a phone book, like I just said, but that is another example of a clustered index. That's because it actually reorganizes the data. That's why you can only have one of those, because a phone book can't be listed A to Z and also by the size of the phone number. See what I mean? It's conflicting. You can't have both at the same time. You can only have, okay, this is sorted by name, or, oh, this is sorted by phone number. You can't have both. Now you could make the phone number size or whatever as a non-clustered index, where it would be like this. It'd have the actual phone numbers in the back, and it would point to where it's located. So at the beginning of the index, it would be like, okay, the phone number that's 00000000001 would be on page 743. The phone number with 00000000002 is on page 242. You see that the actual data isn't organized by the phone numbers, but you can use that non-clustered index that sorts it that way and has a reference to the actual data where it's located. Now, you guys are probably sick and tired of me rambling about this, so let me just explain how this makes sense in databases. Well, when we're working with a database, often we will use a certain column for certain things. And that column will be used frequently, and we want that to be like super fast. So we want the database to know how to use it the best way. So we create an index. The database understands the index, so that way when you tell it to do something, it can do it faster, rather than it having to go through all of the data, which is called a table scan. When you're working with a database with millions of rows, that can take forever. If you have an index, it'll use an index seek, which will basically know where to start searching for that data. That's awesome, because it makes our queries tons faster and saves a lot of resources. There's downsides to it though, because when you create an index, not only does the actual table have to update whenever you update it, but you also have to update the indexes. Think of like a book. When you add something to this book or you change something within this book, not only does the actual book content in the beginning of the book change, but also when you flip to the back, the index must also be updated. Otherwise, all this index information is going to be out of date and useless. So that's a downside to indexes, is when you update your information, it might take a little longer. In a database query, we might say something like select the first name, last name, and the phone number and the email of the user with the user ID of 72, for example. Well, I kind of said that in English, but when you're actually working with a database, it might be more like select first name, last name, email, phone number, where user ID equals 72. That would be an example of a database query. Now that where clause is using the primary key. So basically, the database is going to go through the table, find the person with the user ID of 72, and then display their first name, last name, phone number, and email. Well, that where is using a column that has an index. The primary key is usually the one that's going to have the clustered index, so that's the way it actually sorts the data. So now, it doesn't have to go through the entire table to find the person with the ID of 72. Because imagine if it was just random data thrown in there with no organization. You have 2 billion rows, right? And the database has to go through and find the one individual row with the user ID of 72. Go to the first one, nope, not 72. Second one, nope, not 72. Third one, nope, not 72. And keep going on and on until it finally found the person with the user ID of 72. Basically, that would take forever. But with a clustered index, it knows, well, 72 is going to be in this part of the database. It comes after 60 and comes before 80, because that's the way it's sorted. So it's going to be like, boom, got it, done. That is how indexes kind of work. So clustered indexes are going to be faster and better, but you can only have one. That's usually the primary key, but it doesn't always have to be, depending on the database and what your goal for the database is. The non-clustered indexes, which are like the index in the back of a book, those are still good and they are recommended if you're doing something where you're like, where first name equals John. Now, it has a list of all the Johns and where they're located on the database, or on the table, I guess. That's also a good thing. But you don't want to have an index on something you're not going to be using a lot, because you'll just have to have another thing updated. Another thing, you don't often want to do where clauses, which is like where first name is Caleb, without that column that you're searching being a indexed column, because it can take forever. Another reason for indexes is to increase the speed of joins. So the way the join works is it takes data from one table and then another table and combines it together by the primary key and foreign key connection. So think of a users and comments. So a user posts a comment. So you have a user table and you would have a comment table. And let's just draw rows on here. So we have this guy. I'm just going to draw pictures just because it's funner. So we have 3 people over here. And we have 4 comments on a website or review, or it doesn't really matter. Well, this one comment is posted by one person, and one person can post multiple comments. It's a one-to-many relationship. Well, when we want to output this to where we can review the data, we want to use a join so it's not across multiple tables. Because if you're thinking like, this comment was posted by the user with the user ID of 72, you're not going to know who that is right off the top of your head, because that's a foreign key connection. So rather, you want to replace that 72 with the actual name of that person or the username. That's a join, and it's all done after the database is created. It's all for the query side. So basically, this is what is defined in our database, and we want to output with a join a new table that looks more pretty and easier to read. When we do this, we're going to do something that says the user ID of this the user ID of this table is the same as the user ID in this table. So if a comment has the user ID of 72, we know that it's done by the user with the user ID of 72. That's a foreign key connection, which we've talked about like this entire series, so I'm not even going to explain that anymore. But now down here, in this table, it's going to say Caleb Curry. Then it'll put the comment, and it'll join that. Well, this is also done with a where clause in some cases. For different databases, the terms might be a little different. But basically, that column that you're connecting by, which in this case would be the primary key, needs to be indexed to make it faster. So whenever you're joining a certain column, the 2 tables, the column you're joining should be indexed. You can also have something that's known as a composite index, which is an index that is an index on 2 or more columns. So think of like a first name and a last name, or last name, first name. Now the thing about these is when you use the indexes, so let's say you select where first name equals this and last name equals that, you have to do them both or it's not going to use that index. Now there are exceptions to this. Think for MySQL actually, if you order them in a certain way, like this, if you put an index on the last name and then also the first name, you can do a where clause for both the last name and first name, so finding everybody with the last name Curry and the first name Caleb would be really fast. But the way this is set up, you can also do the leftmost one too. So you could say, find the person with the last name Curry. That's going to work. But in this case, you couldn't do it with the first name because it's not on the left. So that's just the way MySQL has it set up. So different database systems might have it set up differently, where you can't search with them individually, or you can. But most likely, when you make a composite index, you should expect to always use that index by itself. Unless you have it set up to where you make a pretty awesome index that can be optimized to do multiple different queries that you need to do. Like if I'm going to make a ton of queries where I put the last name as the where, and then I'm going to make a ton of queries where I put last name and first name for the where, this would be a good way to set that up because I'm making one index for last name, first name, that can also be used for just last name. So yeah, that's just the basic introduction to indexes. Yeah. I'm not going to be giving you tons of syntax to actually making them because, like you should know by now, this is a database design course. We're just trying to learn how to design our indexes on our tables so that our database works good. So that's something you may have to learn more once you actually program a database, because you can test the speed of the actual indexes to see this for speed optimization to make the database as fast as possible. You can't really do that if you're only designing a database. You can only get so far when designing indexes with the database, but you can get pretty far because, I mean, obviously you'll likely be using the primary key for where clauses and joins, so that's something that's good to have a clustered index on. What a data type is when you create a column. Every single value in that column has to be of a certain data type. So you need to tell that column when you create the database what data type it is to be. Also, when you're designing, you usually put the data types there as well, so that way you have an idea of how your database is going to work. So there's three main categories of data types, and the naming conventions or the names of these data types from one database management system to another database management system might vary a little bit, but in general, they're organized into three main kinds. That's date, numeric, and string. So basically, we're going to be going over these in a little bit of depth. We're not going to go super in depth because right now you just need to understand what these are and just understand that your database application might be slightly different from others. Let's start from the bottom up just to make things fun. String. A string is any characters or like letters. So basically, you put these within quotes. So, hey. This is an example of a string. Even a number within quotes can be used as a string. In this case, this would be used as a string. Basically, the 3 doesn't have any mathematical value unless it's converted to numeric. Within string, you'll often have some subcategories. You'll have something that's either char or varchar, which those just mean character or variable character. What that means is it's just like a list of characters. The character or char usually is stuff that's set in length, so like a phone number or a zip code, something that doesn't change size-wise. So basically with a char, you'll have it something like char 8, and every single value within that char column is going to be stored as 8 individual characters. Now even if you don't put 8 characters, let's say you put 6, then there's going to be 2 blank characters in there, so they're all stored as 8. Varchar, on the other hand, is variable, basically meaning that the size can change. You can have anywhere from 0 up to 8. There's also often the subcategory or sub-data type of text, which is often used for larger things such as comments, messages, and so forth. That's basic summary of the string data types. As for numeric data types, these are numbers. That's different than this. This is a string that has a number in it. That's used differently than the numeric data type. The numeric data type doesn't have quotes, it's just the numbers that you're using. Just like string, there's often some subcategories of decimal and then floating point or double. Decimal works in base 10. Now, I know we haven't really gotten much into bases, and I'm just going to put date back up here since we haven't got there yet. But I think it's really important to know. And in fact, I've made a lot of videos over binary, hexadecimal, and stuff. Basically different numbering systems that use different bases. Well, decimal uses base 10. It's the number system we're used to counting in. You know, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then it goes back to 10. 11, 12, 13, 14. It's base 10. That's what deci means in decimal. Well, there's also binary. So we have decimal and then we have binary. Decimal is base 10. Binary is in base 2. So binary, we only have the options of 0 and 1. Now, you don't really need to understand how to calculate in binary, but if you want to know that, I do have videos for that. But just know when we're working with decimal, it is working with a base 10 system. When we're working with floating points, we're working with binary, which is stored differently. It's stored in binary, and then you can have it presented as decimal for math or whatever. So what's really the difference? Do you use decimal or do you use floating points? It just kind of really depends. Decimal generally is more accurate on mathematics to a point. There are problems that can come up with decimal, but you'll just have to research those. But basically, this one has some errors. Binary, it has problems with certain mathematical equations or numbers. For example, when we want to store 1/4, it's stored like this. We have 0.01. And the way this kind of works is we have anything after the point that divides the number basically in half. So we would have half, but we don't have half. So we have half of a half, 1/4. Kind of makes sense? So the place values would be, this one right here would be, we'd have half. This place value would be 1/4. And then anything after that would be 1/8. And anything after that would be 1/16. So right now, the way we have it, we would take 1/2, multiply it by 0 to get 0, because we don't have anything there. We take 1/4, multiply it by 1, since we have it there, we'd get 1/4. 0, 0. We add those up and we get 1/4. Basic adding and multiplying to understand how it works. But when we have a number such as 0.1 in decimal, that is basically impossible to store in binary, simply because we're working in a base 2 system and we can't get to 0.1 very easily. Because 1/8, that doesn't quite cut it. You'd have to basically have a combination of a bunch of different fractions to get as close as possible to 0.1, but you can never really get there perfectly. So that's a problem with the floating points. So if you needed to store something like that, you would, if it needs to have that accuracy, you would have to have it stored as a decimal, which stores it differently. Oh, that was a lot. Sorry if I completely overwhelmed you with that number stuff. And if I did, don't even worry about it. That was a little too fast. If you need it slower, please check out my introduction to binary video. It's a super long video where I basically explain it step by step so you understand. And then I have a couple other videos adding and subtracting, and also fractions in binary. You will also have an integer type, which will only store numbers that don't have any decimals after them. So only whole numbers, like 5, 12, 28, -52, so forth. With numbers, we also have to worry about whether they are unsigned or signed. If they are unsigned numbers, that means that they can't be negative. If they're signed, that means they can be positive or negative. You're probably wondering, why would you ever do that? Well, if you're working with something that doesn't go negative, well, then you wouldn't need it to have that negative. When you have a signed number, and it can be positive or negative, the range of potential values stays the same, but since you include negatives, the maximum value is different. It's not as high. Think about if you have a range from 0 to 1,000, but then you include negatives, now you have from -500 to 500. That is going to be told with the data type. So you might say something like double unsigned. That would work as a number. That's enough for numbers. I don't want to talk about this anymore. Let's talk about dates. Dates. Well, there's a couple different things you need to know about dates. There's date, then there's time, there's date time, and then there's timestamp. So let's talk about date time first, because it makes sense the best. It basically just stores a date, such as, 02 for February, then you might have a colon, you might have 22 for the date, the 22nd, and then a colon, maybe 1998 for 1998, the year. Then you have the time, which could be whatever. It could be 12, 30, 22, which would be the seconds, and you might even be able to have some milliseconds or microseconds. That's how you would store a date time. The way it actually looks might vary from database management system to database management system. Some might have colons between the numbers, some might have hyphens or commas or whatever. It doesn't really matter. I don't want you to think about that right now. I just want you to think about the date being a date and the time being a time. Date time being the combination of a date and a time. So that's pretty much that for dates. The only other thing is the timestamp. The timestamp is an exact moment in time that's recorded to establish when something was created or done. It can be in milliseconds, or it can be in the month, and the day, and then the second, hour, and then the seconds, and then the milliseconds. Or it can just be a number of seconds, so forth. It varies. But anyways, that's going to give you a number when something was done. It's usually for something like when an account was created, or when a transaction was done, or when something happened. When you update a column, that timestamp will often update, and that's going to keep it to like when that row was entered into the database. So if you enter a new row and one of the columns is a timestamp, it's going to give you a value as soon as you submit that and it's put into the database. The timestamp's created and it says, okay, this row was entered at this time. That's the main thing with timestamps. So basically we've got three types of data types. We've got string, it's numeric, and then date. All of those classifications have different data types for each one, but in general, as long as you know like the gist of what is what, you'll be fine. You don't have to worry too much, because when you get in actually programming a database, you will have more specifics on what data types to use. So this video will be talking about joins, and in fact the next whole group of videos will be about joins. So it's going to be a lot. Now, joins are a complex subject. They can be confusing and tricky and very syntactical. I don't even know if that's a word, but basically the syntax from relational database management to another relational database management system can be confusing and complex, but rather than diving in just learning all that stuff, we're going to be talking about the concepts of what the types of joins are. And I know you might not even know what a join is yet, so you're probably thinking, I don't know what you're talking about. Well, that's what we're talking about today. So, thank you for joining me. Let's begin. So, a join is when you take something that's structured in a database in a confusing, non-user-friendly way, and you're presenting it in a user-friendly way. Now, this is done so that way we can store our data in the database in a way that's the best structured, to where we protect our data integrity and it's normalized and separated across tables with the proper relationships and data types and keys and indexes and everything. But when we actually want to present that data, for example, on a web page or in a program, or to the analyzer person who goes and analyzes and does calculations on our data, or just views those calculations after the database does all the work with the analyzation, well, that end result is often in a way, and it looks in a way that is organized and structured. It makes sense to us. That's the purpose of a join. So it takes a mess and puts it out in a way that looks beautiful. And this can be done over multiple tables. So for example, we could have a table here, and a table here. And these could all be three different tables with relationships between the tables. We won't get into any specifics of what kind of tables, but basically a join is going to take all of this and it's going to present us with a generated table that is more pretty, it's more beautiful and more structured, and it makes more sense. Now the way this is done is using foreign key, primary key connections. So when we have these relationships between these tables, where I drew these arrows here, that represents a foreign key connection that references a primary key. So one of these tables is the parent and one of them is the child. And we want the end result to combine them together into one. Now, when you do this, these columns that are connected are going to be indexed to make it much faster. Now, when you join tables, often you will replace names of things with more user-friendly names. So for example, we could have, let's say we had a comment on a website, and it says, wow, lame. And then this is posted by Caleb. Well, you can see that if you have that username here, it might actually be a user ID in a comment table. So for example, we could say this up here is the comment table, this is the user table, and there's a foreign key from the user ID referencing the user ID in the user table. Well, when we present that data on a database, we will want to replace that user ID with the actual username. So rather than having, we could have it to where it's like user ID of 4,582, and then you're like, oh, I don't really know what that means. Well, since this is all within the comments table, now we're going to take information from the user table and put that username instead of the user ID. That is how a join works conceptually. That's another important thing. All this, think of it conceptually. These videos are going to be helping you understand the concepts of the different kinds of joins. And throughout it, I'll be giving you some examples of how you would type that in SQL maybe, but I'm not going to be getting into the specifics. That's because joins are done differently from database management system to database management system. So what you just need to know is how the joins work and the expected results. And then when you start working with MySQL or SQL Server or Oracle Database or whatever else, then you can just figure out how to do their joins. You'll already know what the results are going to be because you understand the joins, and then you just type it out and boom, you got a join there. Now this is one other thing to know that's important, is all of this is data manipulation. Most of what we've been talking about before is data definition. So that was in basically DDL. But now we're going on to DML. So DDL, data definition language, and data manipulation language. These are two parts of SQL. And we all talked about this in the older videos, but we're on like way farther now, so you guys might have forgot this. But this is important to know, because now we already have the definition, the structure of the database. The database might already be completely designed and structured with the columns and the rows, but now we're manipulating that data to look a certain way. So by doing joins, you're not actually changing the structure of the database. You are changing the presentation of that database. That is extremely important to know. Now you may be wondering, why exactly do I need to know this? Because if I'm a database designer or whatever, really all I need to do is design the structure of the database, and then the database administrator or the software engineer person or whoever can go in there and use my database that I designed and created, and they can do all the data manipulation stuff to fit their application, right? Well, maybe, but not likely. That's because the joins are also very important to understand, because when you design your database, you need to think of it in a user-friendly way and then normalize it, make it confusing, and then present it in a user-friendly way. It's kind of confusing because you start with, let's say you're really bad at database design and you're structuring a table and you have it to where it's like comments, comment table. And within this you have a user name, and then you have the comment, and then maybe the blog post or video or whatever. It doesn't really matter. You can have some IDs in there. Basically, you don't know what you're doing, and you put the username. We'll just go with Caleb C. Comment lame. Then we got another one from Caleb C. Cool. And Caleb C. Awesome. When you look at this and you show it to your grandma, she understands it. She's like, okay. She might not understand it, but she gets, if you explain it, she might. Caleb C. posted the comment lame. Caleb C. also posted the comment cool. Caleb also posted the comment, Caleb C. also posted the comment awesome. But this isn't the best way to do this, because we learned about data integrity. and also repeating data, because now we have this in here 3 times. So instead we use a user ID, we get rid of Caleb C, and we get rid of the username, we have the user ID, and then in here we have the user ID 6, let's not use that number, 777, and then over here we have a user table with the user ID column, which has all of our user IDs for each individual person. So we started off with this friendly design, but in reality it doesn't work because it's not normalized, there's repeating data, but it looks pretty. Once we have that, then we can break it up and normalize it, so that way we have multiple tables. So we have this table, and then we have this table over here. But that's not the only thing we do. The next thing we have to do is you have to take up those pieces of the puzzle and put them back together in a join to get the final result. So we basically want to replicate the original table we had here by using a join of our normalized database and recreating it. So what we're going to do is we're going to take the user ID column, and we're going to take the user ID. Can you guys see that all good? It's over there. This will likely also have a username column, so I kind of ran out of room here. But username, and that user ID of 7 will be connected to Caleb C. Using a join, we are going to connect these two tables by basically using this foreign key, which points to 7, and finding the associated username with that user ID, and our join will look like this. Username, comment. And the name of the table can be, I mean, whatever you want. It can be generated table. Or it doesn't even need a name if you're just putting it on a website or something. And then under the username column, it'll be Caleb C. And then Caleb C. And then Caleb C. And then under the comment, you're going to have lame. And cool. And awesome. But this wasn't just like this to begin with. We got the username from this table, and we got the comment from this table. So not only do you have to design the structure of the database, but you have to structure the joins to basically put our database back into simple language or grandma readable tables. Okay? That's basically what we want to do. So let's say you get a job or you're working for a developer or something, and they say, okay, on my website, I want a table on this users page where I can sign in with my username, password, and I can see their username, their password, their email, their date they signed up, and everything like that. And if I want, I can go in there and edit it. That way, they don't have to go in and type SQL. You're going to have that programmed in the actual application to send that SQL. But we need to structure the tables. We need to make a join that's going to be able to combine those all to one pretty table, which that's the job of the database designer, likely. I mean, if the applications or the database is huge, you might have someone who does the designing, and then someone who does the implementation, and then someone who does the joins, and then someone who does this other junk. But I mean, if you're just working on your own and you gotta do everything, you're also gonna have to design the joins. And I highly recommend you do that before you go in and programming your application. And then you're like, oh crap, I don't know how to do this, or oh, my database is structured wrong. You want to do this all beforehand. Don't rush into things, because then you're gonna be like, dude, dog, my application ain't working right. And the reason is because you didn't take the time to structure your database the right way and develop your joins. Man. Okay, once you got that, you're good to go. And yeah, so there are a couple different kinds of joins. There's inner joins, outer joins, cross joins, unions. There's all kinds of different things that we're going to be talking about. Okay, so the way an inner join works is it's going to take one table and another table, and then wherever there is rows from this table and this table that are connected, it's going to present them in a new generated table. So let's just break this down and see how it works. Let's go with an example, right? Because you gotta use examples. We're gonna have a customer table, and we're also going to have a card table. So think of like a bank, for example. You're going to have a customer table where you're going to put all your customers in there, and then you have a card table where you're going to put every single card that's been given out or will be given out to people who have credit cards. Or you could make it to where you can even include debit cards in there, but we'll just worry about credit cards for now. So basically, we're going to draw this out, and we're not going to have it required that a card has a customer or a customer has a card. So neither of these columns are going to be labeled as not null. So basically, the card does not need to have a customer, and a customer does not need to have a card. So we'd have one table over here, and another table over here. And generally this would be designed as a one-to-many relationship, because one person can have many cards, and usually one card is owned by one person. You could design it as a many-to-many relationship where you can joint own a card or multiple people can own a card, but you can modify the examples as needed. So let's say this is the customer, and this is the card table. Now we might have something like, of course we're going to have an ID for the customer, so we're going to have the customer ID. You know, their first name, last name, their address, their date of birth, all their personal information that we need for their data for the bank. That's where that's going to go. Over here, we're going to have a card ID, and then we're also going to have a customer ID. And because this is a one-to-many relationship, we have the child and the parent. If this is a one-to-one relationship, we could have it to where there was also a card ID in the customer table if we wanted. But I'm not going to do that. And we can get into one-to-one relationship design best practices in another video. But for now, the customer ID is going to reference this customer ID. And here we can also have more information about the card. We could have the total amount, or the limit, max amount I guess I could say.